Hey guys, today we are going to solve the problem Kth smallest element in a sorted matrix. In this problem we are given an n by n matrix and we are also told that each of the rows and the columns is sorted in ascending order. And we are asked to return the K smallest element in the matrix. So how could we do it? The first thing that I like to do when I'm looking at a matrix problem is to think what would I do if it was just a 1 by n matrix, or in other words, just a simple list. So if I had a sorted list, I would simply return the element at the kth index. But we don't have a list, we have a matrix. Well, how could we convert this matrix to a list? One thing we could do is to initialize pointers to each of the lists. So we would have a pointer that currently points here, another pointer that currently points here, and another pointer that currently points here. And we would ask which one is smaller. Well, in this case, 1 is smaller. So we would put 1 and move this pointer to the next index. Now, again, we do the same process. We move the first pointer and put here this element, and again. And now we are left with only 2 pointers. We're going to ask which one is smaller. We're going to put 10 and keep going, right? So this is one option to build such a sorted list from a matrix like we got. What would that cost us? That would cost us n, because each time we have to check each of those n pointers, times the amount of elements in the array, in the matrix, So it would total in O of n to the power of 3 time, and the space complexity would be O of n squared, because that is the amount of elements in the matrix, and that is also the amount of the array that we are building. But the first thing to notice is that we don't actually need the array. We are just looking for the kth element. So it's enough to count how many elements we've already inserted, in quotes, to the array. And when this counter reaches k, then we know that we can return the answer. And we don't actually need to keep this array. So the space complexity could actually be lowered to constant. Time complexity is still not so great. So how could we improve the time complexity? Notice that each time we asked ourselves which pointer points to the smallest element. And we had to iterate over all of the n pointers. But there is a more efficient way to do that. We could use a data structure called a min heap. Let's do one quick example. Okay, imagine that we have this matrix. What we are going to do is we are going to keep a minimum heap, and for each element in the heap, it's going to be a triplet. One for the value of the number. Second is which row did this number came from. And third, it's going to be the index in the row, so the column. What does that mean and how does it help us? So, as we said, each time we want to compare the smallest current element from each list. So in the beginning, it's going to be 1, 10, and 12. So our heap is going to look like this. It's going to have one element, which value is 1, its row is 0, and its column is also 0. Our second element is going to be 10, 1, and 0. And the third element is going to be 12, 2, and 0. And now, given this minimum heap, we want to pop the minimum element, or the element with the minimum value. When we pop the element, we are going to get value 1, row 0, and column 0. So we know that the minimum element came from the first row, because it was row 0, and it was in the first column, because the column was also 0. So what that tells us is that we have to insert to the heap the next element in that row, which in this case is 15. So now we are going to insert to the heap 15, 0, and 1. And this way, every time we can keep the smallest element from each row in our heap, and this way we can simply build the list that we were talking about earlier. Or again, we don't have to build the list, we just need the values, and we just need to keep count of how many elements we've already popped from the heap. So you can see this way, each time we'll get the smallest element. So let's just keep iterating over the algorithm. Now 10 will be popped, and we are going to insert 11, and let's say we are looking for the third smallest value. So we've already popped two values, and now we are going to pop 11, and because we've popped three values now, 11 is our answer. What is the time complexity and space complexity of this algorithm? In the beginning, we initialize the heap to have the first elements from each row. That will cost us n time. After that, we have to pop k times from the heap, and the size of the heap is always n. So it is going to be logarithmic in n. This is the total runtime of this algorithm. And for the space, we are using extra space for the heap, and the size of the heap is again always big O of n. So this is the runtime and space complexity of this algorithm. I will try to keep the variable names the same as we did in the explanation. So first of all, we want the length of the matrix. And now we want to create the heap, and we want it to contain the first element from each row. So for every row in the matrix, what we want to do is we want to append to the heap the value. Remember, we want triplets of value and row and column. So that's simply going to be okay, because the column is 0, because that is the first element. Now we want to actually convert this list to a heap. Now that we have the heap, all we want to do is we want to keep popping elements until we've popped k elements. So to do that, we will keep track of how many elements we've popped. And while we didn't remove k elements, we want to continue. Okay, so after we've popped an element, what we want to do is we want to insert the element from the row we've popped, but from the next column. So, for example, if we popped this element, we want to insert the next one to the list. So, which element are we going to insert? We are going to insert the element from the same row, but from the next column. But we also have to check if we are still in bounds, because if we popped, for example, 9, we can't insert the next element because it doesn't exist. And I think that should be it. Let's just return the value. And this should work. Seems like it does.